Hello to all my dear students. It is such an immense pleasure to be back with you today. You see me with a big smile because we are about to start an exciting part of our curriculum together. After solidifying our knowledge during the previous sessions on analysis, we are now diving straight into the heart of the action with this second term exam topic, specially designed for you, the cream of the crop of the math track. Come on, everyone, let's see some energy. Take a good look at this first slide. We are going to break down this first exercise on probability like true professionals. First, the context, our sample space. Look at this jar on the left. It's our starting point. We have a total of 5 balls that are indistinguishable by touch. This is crucial because it guarantees equal probability. We have 2 white balls labeled W1 and W0, 1 green ball, G-1, and 2 red balls, R1 and R2. Now look closely at the condition box. This is where everything is decided. It mentions successive draws without replacement. What does that mean for us? It means that order is vital and there is no repetition. That is why the cardinality of our sample space omega is calculated as a permutation. Cardinality of omega equals P5, 2, which gives us 20 possible outcomes. Keep that number 20 in mind. It's our common denominator for everything that follows. Second, the mission, our mathematical challenges. Let's move to the right side now, our roadmap. I want you to be focused and methodical. The probability tree, our first step will be to build a complete tree. It's our map so we don't lose any outcomes along the way. Imagine each branch as a path leading to a possible result. Event A, we will need to calculate the probability of getting 2 balls of different colors but with the same number. It's a tricky little trap, but I know you'll navigate it brilliantly. Random variable x, this is where the exercise becomes truly elegant. Look at this diagram with the 2 arrows. The definition of x depends on the color. If the balls are the same color, x is the product of their numbers. If the balls are different colors, x is the sum of their numbers. It's brilliant, isn't it? It forces us to clearly separate our cases. Third, moving toward the conclusion of the exercise. Once we have determined all the possible values of x, we will establish its probability distribution in table form. This is the very structure of our reasoning. Finally, we will look for 2 fundamental values, a little riddle involving the calculation of x squared plus 1 equals 5x, which will give us the.
We are now diving into the vibrant heart of analytical geometry, barycenters. On our graph, we have a well-defined triangle ABC in an orthonormal coordinate system. Look closely at the positions. Point A, 20, and point B, -50, are anchored on the x-axis. Point C06 sits proudly on the y-axis. It is an ideal configuration for understanding how mass and position interact. Come on, class, let's see some energy. We are going to solve this with elegance and precision. Mission 1. The search for point G, the perfect balance. We are asked to calculate the coordinates of point G, the centroid of triangle ABC. Remember, the centroid is what we call the isobarycenter. It is the point where the 3 vertices carry the same weight, the same influence. Mission 2. The challenge of the partial barycenter H. Now, let's focus. We need to find H, the barycenter of the system A2, C-1. Careful here, the coefficients are changing. Point A weighs twice as much, while point C has a negative influence. It's like a geometric tug-of-war. Mission 3. The graphical realization. This last step is my favorite. It consists of plotting these points on our graph. It's the moment of truth. By placing G-1, 2 inside the triangle and H4, -6 in the bottom right, you will see the visual logic of your calculations. Geometry never lies when you treat it with respect. We are going to dive into exercise 1, and more specifically, the first question regarding event A. The goal here is very precise. We need to draw 2 balls that meet 2 simultaneous criteria. First criterion, they must be different colors. Second criterion, they must have the same number. It's like looking for twins dressed in different colors. You see the idea? Let's take a close look at the diagram in the upper right. We have a set of 5 balls, a white ball numbered 1, W1, a white ball numbered 0, W0, a green ball numbered -1, G-1, a red ball numbered 1, R1, and a red ball numbered 2, R2. Now, let's put those sharp observational skills of yours to work. Which numbers repeat? The only number appearing on 2 balls of different colors is the number 1. We have the 1 on the white ball, W1, and the 1 on the red ball, R1. The other numbers, 0, -1, and 2, are unique in this urn. Therefore, to achieve event A, there is only one possible pair of balls, the white one and the red one. Since the drawing order matters here, given that we are calculating based on a total of 20 possible outcomes, we have two favorable arrangements, either drawing the white then the red, W1, R1, or the red then the white, R1, W1. This explains the result you see so carefully written down. The cardinality of A, denoted card of A, is equal to 2. This is the number of outcomes favorable to our event. To wrap up this step brilliantly, let's calculate the probability P of A. It's child play if we stay focused. We divide the number of favorable outcomes by the total number of possible outcomes, the sample space. P of A equals 2 divided by 20. By simplifying this fraction, we get 1/10, which...
Before we continue with the video, don't forget to subscribe, like, and share the video. And leave a comment, as it encourages us to keep creating this kind of content. Together, we are going to break down how this variable x takes its values based on two very specific conditions. Think of it as a game. All you have to do is follow the rules with precision and flair. Number 1, the rules of the game. Same color or different colors. Our variable x behaves differently depending on the draw. We have two distinct rules. If the balls are the same color, we calculate the product of their numbers. If the balls are different colors, we calculate the sum of their numbers. Crystal clear, right? Come on, let's keep this momentum going. Number 2, the first case, balls of the same color, the product. Let's look at our scenarios on the left side of the image. Scenario 1, the whites. We draw two white balls, W1 and W2. Look at the operation. 1 times 2 equals 2. So in this specific case, our variable x takes the value 2. Scenario 2, the reds. We draw two red balls, R1 and R2. Here, the calculation gives us 1 times 0 equals 0. Therefore, the value of x is 0. Take note of this trick, my dear students. Look at the bottom in yellow. This is crucial. There is only one green ball. Therefore, it is technically impossible to draw two green balls. This scenario doesn't exist. It's pure mathematical logic. Number 3, the second case, different colors, the sum. This is where our table gets very interesting. We're no longer multiplying, we're adding. White-green combination. If we take the white W1, number 1, and the green G, number -1, the sum 1 plus -1 gives us 0. If we take the white W0, number 0, and the green G, number -1, the sum 0 plus -1 gives us -1. Red-green combination. With red R1, number 1, and green G, -1, we get 0. With red R2, number 2, and green G, -1, we get 1. White-red combination. This one offers the most possibilities. W1, 1, plus R2, 2, equals 3. W0, 0, plus R1, 1, equals 1. W0, 0, plus R2, 2, equals 2. Conclusion of this step. You see, by analyzing each case methodically and with a little passion, we have identified all the possible values for our random variable x. We are now armed and ready to build our probability distribution in the next step.
Take a good look at the table at the top of your screen. Here we have a random variable x that can take 5 distinct values, -1, 0, 1, 2, and 3. For each value xi, we have an associated probability, p of x equals xi. Notice the precision. The total sum of these probabilities, 0.1 plus 0.3 plus 0.2 plus 0.3 plus 0.1, is exactly equal to 1. That is the golden rule, class. Never forget it. Now, let's move on to the most exciting part, solving the equation x squared plus 1 raised to the x equals 5 to the x within the context of our random variable. We need to test the values of x present in our table. Case 1, x equals 0. If we substitute 0 for x, we get 0 squared plus 1 raised to the 0 equals 5 to the 0, which comes out to 1 equals 1. That is perfectly true. So x equals 0 is an accepted solution. Case 2, the bases are equal. If the exponents are the same, we can set the bases equal to each other. X squared plus 1 equals 5, which leads us to x squared equals 4. Here we have two mathematical possibilities, x equals 2 or x equals minus 2. Look closely at our original table. Does minus 2 exist? No. That is why the value minus 2 is rejected. On the other hand, x equals 2 is indeed present in our probability distribution, so it is accepted. Now let's move on to calculating the expected value e of x. The expectation is a bit like the average we would get if we repeated the experiment an infinite number of times. It is the center of gravity for our distribution. The formula is elegant. E of x equals sum xi pi. Follow the detailed calculation on the image carefully. We multiply each value by its probability. Minus 1 times 0.1 plus 0 times 0.3 plus 1 times 0.2 plus 2 times 0.3 plus 3 times 0.1, which gives us minus 0.1 plus 0 plus 0.2 plus 0.6 plus 0.3. The final result is e of x equals 1. It's a beautiful and clear result, isn't it? To finish on a high note, if you are asked for the probability that this equation holds true, we simply add the probabilities of the solutions we found. P of x squared plus 1 raised to the x equals 5 to the x equals P of x equals 0 plus P of x equals 2. Looking at the table, we see that P of x equals 0 equals 0.3, and P of x equals 2 equals 0.3. The final result is therefore 0.6.
Take a good look at the table at the top of your screen. Here, we have a random variable x that can take 5 distinct values, -1, 0, 1, 2, and 3. For each value xi, we have an associated probability p of x equals xi. Notice the precision. The total sum of these probabilities, 0.1 plus 0.3 plus 0.2 plus 0.3 plus 0.1, is exactly equal to 1. This is the golden rule, my children. Never forget it. Now, let's move on to the most stimulating part, solving the equation x squared plus 1 to the x equals 5 to the x within the context of our random variable. We need to test the values of x present in our table. Case 1, x equals 0. If we substitute 0 for x, we get 0 squared plus 1 to the 0 equals 5 to the 0, which boils down to 1 equals 1. This is perfectly true. So x equals 0 is an accepted solution. Case 2, the bases are equal. If the exponents are the same, we can set the bases equal to each other. X squared plus 1 equals 5, which leads us to x squared equals 4. Here, we have two mathematical possibilities, x equals 2 or x equals -2. Take a close look at our initial table. Does -2 exist? No. That is why the value -2 is rejected. On the other hand, x equals 2 is indeed present in our probability distribution, so it is accepted. Now, let's move on to calculating the expected value e of x. The expected value is a bit like the average we would get if we repeated the experiment an infinite number of times. It is the center of gravity of our distribution. The formula is elegant. E of x equals sigma xi times pi. Follow along with the detailed calculation on the image. We multiply each value by its probability. -1 times 0.1, plus 0 times 0.3, plus 1 times 0.2, plus 2 times 0.3, plus 3 times 0.1. This gives us -0.1, plus 0, plus 0.2, plus 0.6, plus 0.3. The final result is e of x equals 1. It's a beautiful and clear result, isn't it? To finish on a high note, if you are asked for the probability that this equation is satisfied, you simply need to add the probabilities of the solutions we found. P of x squared plus 1 to the x equals 5 to the x equals P of x equals 0 plus P of x equals 2. Looking at the table, the final result is therefore 0.6.
We're going to tackle exercise number 2, which deals with a fundamental concept, the center of gravity. First, look at the graph on the left, titled Initial Parameters. We're in a standard Cartesian coordinate system. Do you see our 3 points? We have point A located at 2, 0, sitting proudly on the x-axis. Point B, on the opposite side, is at -5, 0. And finally, point C, peaking on the y-axis at 0, 6. These 3 points form a triangle, and our goal is to find point G, the center of gravity, also known as the centroid. Imagine this triangle is a physical plate. Point G is the exact spot where you could balance this plate on the tip of a pen. It's beautiful, isn't it? To find the coordinates of point G, the method is elegantly simple. It's the arithmetic mean of the coordinates of the vertices. We add everything up and divide by 3 because we have 3 points. Follow me closely through the calculation. Pay close attention. 1. For the x-coordinate, xg, we take the x-coordinate of A, 2, add that of B, -5, and that of C, 0. 2 plus -5 plus 0 gives us -3. We divide by 3, and presto, we get -1. 2. For the y-coordinate, yg, we do the same with the y-coordinates. 0 for A, 0 for B, and 6 for C. 0 plus 0 plus 6.
Before we continue with the video, don't forget to subscribe, like, and share the video. And leave a comment, as it encourages us to keep creating this kind of content. The study of barycenters is a powerful tool. As you will see, it is almost like mathematical magic. Take a good look at this slide, my dear students. We are going to tackle exercise 2. To succeed, you must always start by observing the data carefully, with calmness and precision. On the left side, we have our initial parameters. Look at this orthonormal coordinate system. We have placed 3 points there. Point A is at 2, 0, point B is at -5, 0 on the x-axis, and point C stands at 0, 6 on the y-axis. Visualize these positions clearly, for they are the foundation of our work. Now, let's focus on the objective. We need to determine the coordinates of point H, but be careful. H is no ordinary point. It is the barycenter of the weighted system composed of C, -1, and A, 2. Before you reach for your calculators, remember the golden rule I often repeat in class, the existence of the barycenter. Look at the little green bubble on the right. We check the sum of the coefficients. 2 plus -1 equals 1. Since this result is not 0, we have the green light. Point H exists and it is unique. It's fantastic, isn't it? Now let's move on to the calculations with all the energy and rigor that define you. To find the x-coordinate, xh, we apply the weighted average formula. We take the x-coordinate of A multiplied by its coefficient 2, and we add the x-coordinate of C multiplied by its coefficient -1. The whole thing is divided by the sum of the coefficients, which is 1. Look at the steps. xh equals 2 times 2 minus 1 times 0 divided by 1, which equals 4 minus 0, which equals 4. There is our first coordinate. For the y-coordinate, yh, it is the exact same intellectual gymnastics. We multiply the y-coordinate of A by 2 and the y-coordinate of C by -1. This gives us yh equals 2 times 0 minus 1 times 6 divided by 1, which equals 0 minus 6, which equals -6. And there you have it, my dear students. We have succeeded brilliantly. The final result is boxed in bright green. Point H has the coordinates 4, -. Together, we are going to discover the nature of this set, sigma. Take a good look at the screen. We have this impressive vector equality. The magnitude of vector MA plus vector MB plus vector MC is equal to the magnitude of 3 vector MA minus 3 vector MB. Don't be intimidated. We are going to break this down elegantly. On the left side of the equation, it's wonderful. Since G is the centroid of our triangle, we use that fundamental property you know by heart. The vector sum MA plus MB plus MC simplifies quite simply to 3mg. That is the magic of the centroid. It reduces complexity into a single vector. On the right side of the equation, we have 3 vector MA minus 3 vector MB. We factor out the 3, which gives us 3 times vector MA minus vector MB. And here, my dear students, remember your basics. Vector MA minus vector MB is nothing other than vector BA. It's smooth, isn't it? Now let's look at the equivalence. We are left with the equality of magnitudes. The magnitude of 3mg is equal to the magnitude of 3BA. In terms of distance, this means that 3mg is equal to 3BA. We simplify by 3, and what are we left with? mg equals BA. But what is the value of this distance BA? Look at the calculation in the center of the image. We use our coordinates. A equals 2, 0, and B equals -5, 0.
BA equals the square root of XA minus XB squared plus YA minus YB squared, which equals the square root of 2 minus minus 5 squared plus 0 minus 0 squared, which equals the square root of 7 squared. And there it is. The result is in. BA equals 7. Now let's think about this together with enthusiasm. If point M moves in such a way that its distance from the fixed point G is always equal to 7, what does that trace? Look at this perfect diagram at the bottom of the page. Point G is at the center, and point M revolves around it at a constant radius r equals 7. It's geometrically obvious. Therefore, the set sigma is the circle with center G and radius 7. It's brilliant, don't you think? We have transformed a complex vector equation into a simple and perfect geometric figure.
The study of set gamma. Don't let these vectors and double norm bars intimidate you. Approach this with serenity and method, just as we always do. We have an equality of norms. The norm of MA plus MB plus MC is equal to 3 times the norm of 2MA minus MC. Our mission is to discover what geometric figure is hidden behind point M. First, let's analyze the left-hand side. Look at this vector sum, MA plus MB plus MC. If you remember our first exercise, we established that G is the centroid, the barycenter of points A, B, and C. Consequently, this sum simplifies beautifully into 3 times mg. That is the magic of vector reduction. Now, let's turn to the right-hand side. Here, we introduce a new strategic point. Let's call it H. This point H is defined as the barycenter of the weighted points with coefficients 2 and minus 1. Why is this brilliant? Because by using the fundamental property, the combination 2MA minus MC becomes equal to 1 times MH, which simply gives us MH. Don't forget the coefficient 3 multiplying the whole expression. Look at the logical transition in the middle of the image. This is where everything becomes clear. The equation becomes the norm of 3 times mg equals 3 times the norm of mh. By simplifying by this number 3 on both sides, we reach a conclusion of absolute simplicity. mg equals mh. My dear children, think for a moment. What does it mean mathematically that the distance between m and g is always equal to the distance between m and h? That is exactly what the little diagram in the bottom right shows us. If point M must remain equidistant from 2 fixed points G and H, then it has no choice but to move along a very specific line. This set gamma is the perpendicular bisector of segment GH. Do you see that blue dashed line on the graph? That is the solution to our puzzle. Perfectly